Grounding and bonding are essential concepts in electrical systems, and understanding them is crucial for safety and code compliance. Grounding provides a path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to trip and de-energize the circuit, preventing electrical shock hazards and minimizing equipment damage. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same electrical potential, further reducing the risk of shock. Let's delve into the details. Firstly, let's look at the purpose of grounding. The primary purpose of grounding is to provide a low impedance path for fault current to flow back to the source. This low impedance path is crucial for the quick and reliable operation of overcurrent protection devices. When a fault occurs, such as a short circuit between a live conductor and a metallic enclosure, a large fault current will flow through the grounding system. This high current will quickly trip the circuit breaker or blow the fuse, disconnecting the circuits and preventing a dangerous electrical shock. Secondly, we can discuss the types of grounding. There are two main types of grounding: system grounding and equipment grounding. System grounding refers to the grounding of the neutral point of a power supply, such as a transformer or generator. This type of grounding helps to stabilize the voltage and reduce the risk of overvoltages. Equipment grounding, on the other hand, refers to the grounding of non-current carrying metallic parts of electrical equipment, such as enclosures, conduit, and motor frames. This type of grounding provides a path for fault current to flow back to the source in the event of a fault. Thirdly, let's mention bonding. Bonding is the process of connecting all metallic parts of an electrical system together to create an electrically conductive path. This ensures that all metallic parts are at the same electrical potential, minimizing the risk of shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect metallic parts together. Fourthly, let's describe grounding electrodes. The grounding electrode is a conductive object that is buried in the earth and used to establish a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The National Electrical Code, or NEC, specifies the requirements for grounding electrodes, including the minimum size and type of electrode, as well as the depth at which it must be buried. Fifthly, we can mention the grounding electrode conductor. The grounding electrode conductor, also known as the GEC, is the conductor that connects the grounding electrode to the electrical system. The GEC must be sized according to the NEC, and it must be properly protected from physical damage. The size of the GEC is based on the size of the service entrance conductors. Sixthly, we can mention the equipment grounding conductor. The equipment grounding conductor, also known as the EGC, is the conductor that connects the non-current carrying metallic parts of electrical equipment to the grounding system. The EGC provides a path for fault current to flow back to the source in the event of a fault. The EGC must be sized according to the NEC, and it must be properly protected from physical damage. Seventhly, we can discuss the ground fault circuit interrupter, or GFCI. A ground fault circuit interrupter is a device that is designed to protect people from electrical shock. A GFCI monitors the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that some of the current is leaking to ground, which could be a sign of a ground fault. When a ground fault is detected, the GFCI will quickly trip the circuit, disconnecting the power and preventing an electrical shock. GFCIs are required in many areas of the home, such as bathrooms, kitchens, and outdoor receptacles. Eighthly, let's talk about surge protection. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line surges. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at individual pieces of equipment that are particularly sensitive to voltage surges. Ninthly, we can discuss the National Electrical Code. The National Electrical Code is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is updated every 3 years, and this is adopted by many states and local jurisdictions. The NEC contains detailed requirements for grounding and bonding, including the size and type of grounding electrodes, the size of grounding conductors, and the bonding of metallic parts. Tenthly, we can discuss some best practices for grounding and bonding. Firstly, always follow the requirements of the NEC. Secondly, use high-quality grounding and bonding materials. Thirdly, ensure that all connections are clean and tight. Fourthly, protect grounding conductors from physical damage. Fifthly, regularly inspect grounding and bonding systems to ensure that they are in good condition. Proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC and implementing best practices, you can help to protect people from electrical shock and prevent equipment damage. Here are some additional points to consider. Firstly, the importance of low impedance. A low impedance ground path is crucial for the fast and reliable operation of overcurrent protection devices. Impedance is the opposition to the flow of alternating current. A high impedance ground path will impede the flow of fault current, which can delay the tripping of the circuit breaker or fuse. This can increase the risk of electrical shock and equipment damage. To minimize impedance, use short, straight grounding conductors and ensure that all connections are clean and tight. Secondly, the role of the neutral conductor. In a typical electrical system, the neutral conductor is grounded at the service entrance. This grounding of the neutral conductor helps to stabilize the voltage and provide a return path for current. However, it is important to note that the neutral conductor is not a grounding conductor. The neutral conductor carries current under normal operating conditions, while the grounding conductor only carries current during a fault. Thirdly, the use of separate grounding conductors. In some cases, it is necessary to use separate grounding conductors for different parts of an electrical system. For example, a separately derived system, such as a generator or transformer, may require its own grounding electrode and grounding conductor. This is to ensure that the grounding system is properly sized and that there is no objectionable current flowing in the grounding conductors. Fourthly, the importance of proper labeling. All grounding and bonding conductors should be properly labeled to identify their purpose. This will help to prevent confusion and ensure that the grounding system is properly maintained. The NEC requires that all grounding and bonding conductors be identified with a green color or a green color with one or more yellow stripes. Fifthly, the need for regular inspections. Grounding and bonding systems should be regularly inspected to ensure that they are in good condition. Inspections should include checking the condition of grounding electrodes, grounding conductors, and bonding connections. Any damaged or corroded components should be replaced immediately. Sixthly, the effect of corrosion. Corrosion can significantly increase the resistance of grounding connections. Corrosion occurs when metal is exposed to moisture and air. This can cause the metal to rust or corrode, which can increase the resistance of the connection. To prevent corrosion, use corrosion-resistant materials and protect grounding connections from moisture. Seventhly, the function of exothermic welding. Exothermic welding is a process that uses a chemical reaction to create a permanent, high-quality electrical connection. Exothermic welding is often used to connect grounding conductors to grounding electrodes. This process creates a strong, corrosion-resistant connection that will last for many years. Eighthly, the NEC Table 250.122. NEC Table 250.122 provides the minimum size requirements for equipment grounding conductors based on the size of the overcurrent protective device. This table is essential for ensuring that the equipment grounding conductor is large enough to safely carry fault current. Ninthly, the NEC Article 250. NEC Article 250 covers the requirements for grounding and bonding in electrical systems. This article provides detailed information on the types of grounding systems, the size of grounding conductors, and the bonding of metallic parts. Tenthly, the role of a qualified electrician. Grounding and bonding are complex topics, and it is important to have a qualified electrician perform all grounding and bonding work. A qualified electrician will have the knowledge and experience to ensure that the grounding system is properly installed and that it meets all applicable codes and standards. 11thly, let's cover the specific example of grounding a subpanel. When installing a subpanel, it is important to properly ground and bond it to the main electrical panel. The grounding conductor from the subpanel should be connected to the grounding bus in the main panel. The neutral conductor from the subpanel should be isolated from the subpanel enclosure and connected to the neutral bus in the subpanel. A separate equipment grounding conductor should be run from the subpanel to any metal enclosures or equipment that are connected to the subpanel. 12thly, let's mention the grounding of generators. Generators require specific grounding configurations depending on whether they are separately derived systems or not. Separately derived systems need a grounding electrode system, while non-separately derived systems may use the existing building grounding system. Consult NEC Article 250 for detailed requirements. 13thly, let's discuss grounding in hazardous locations. In hazardous locations, such as those containing flammable gases or vapors, grounding and bonding are even more critical. The NEC has specific requirements for grounding and bonding in hazardous locations to prevent explosions and fires. 14thly, let's look at grounding for sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, may require special grounding techniques to prevent noise and interference. These techniques may include the use of isolated grounding conductors and shielded cables. 15thly, let's look at grounding and bonding in existing buildings. When working on electrical systems in existing buildings, it is important to ensure that the grounding and bonding system is up to code. If the existing grounding system is inadequate, it may need to be upgraded to meet current standards. 16thly, let's discuss the importance of documentation. All grounding and bonding work should be properly documented. This documentation should include the size and type of grounding conductors, the location of grounding electrodes, and the results of any grounding tests. 17thly, let's mention the use of ground testing equipment. Ground testing equipment can be used to measure the resistance of the grounding system. This can help to identify potential problems with the grounding system, such as corroded connections or damaged grounding electrodes. 18thly, let's cover the concept of static electricity. Static electricity can build up on non-conductive surfaces, such as carpets and clothing. This static electricity can discharge and cause a shock. Grounding and bonding can help to reduce the buildup of static electricity. 19thly, let's look at grounding and lightning protection. Grounding is an important part of a lightning protection system. A lightning protection system is designed to protect buildings from lightning strikes. The grounding system provides a path for the lightning current to flow safely to ground. 20thly, let's discuss the impact of improperly installed grounding system. An improperly installed grounding system can be ineffective and even dangerous. It can increase the risk of electrical shock and equipment damage. Therefore, it is important to have a qualified electrician perform all grounding and bonding work. In summary, proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC and implementing best practices, you can help to protect people from electrical shock and prevent equipment damage. Remember to consult the NEC and a qualified electrician for specific guidance on grounding and bonding in your particular situation. And finally, always prioritize safety when working with electricity.